dark matter coming from measurements of light nuclei abundances. I'm going to say axion in the course of the talk all the time, but what I really mean is axion-like particles. It's not the pure QCD axion where the mass is related to the coupling to the QCD scale. And we'll see this in more detail as we go on. So I will first start with a very basic introduction to the strong CP problem and the properties of axion dark matter. Then I will present the main result of the talk that has the quality of being very simple, so you can just state it and show the 3 physical reasons why it works and push all the technicalities towards the end. So this is really the main result, and then I will go on discussing the details. In particular, how we can link the axion coupling to gluons to an effect during the nucleosynthesis, and how a large fraction of axion dark matter parameter space is very severely tuned, even though many people do not mention it because, I mean, it goes in their interest not to mention it. And then after all that, I will just flash very briefly an idea on how to convert axion experiments to gravitational wave experiments, and conclude with some prospect and possible future ways to expand this work. Okay, so let's start with the very basic introduction. As you know, there's this term in the QCD Lagrangian that is CP violating. It couples the muon field strength with its dual, and if you do all the CHIRAL Lagrangian gymnastic that was done several decades ago, you see that this term induces a neutron electric dipole moment, and you can measure such a dipole moment in current experimental bounds once for this parameter, this dimensionless parameter in the QCD Lagrangian, to be of order 10 to the minus 10. So there's no reason why this parameter shouldn't be order 1, and it's very unsatisfactory to just fix it to bit 0. So there's one case in which this parameter really doesn't matter, and it's the case in which the QCD vacuum is topologically trivial. But if this was really the case, there would be a problem with the eta meson mass, so we cannot just ignore this term. We could fix by the coefficient to be 10 to the minus 10, but of course, this has never appealed to any theorist. Also because there are at least 3 ways of having a small value naturally, or have a small effect in the EVM naturally. Probably the most popular solution is to add a global symmetry that is spontaneously broken at some scale that I'm going to call FA. If this symmetry is anomalous under QCD, then the Goldstone boson associated to the spontaneous breaking will acquire a potential due to the QCD anomaly that is precisely proportional to the term that we would like to cancel. If this is the only source of potential for this particle, that is the axion, then the minimum of this potential will sit naturally on the value that cancels the constant piece that we want to make small. So this is a very natural dynamical way of trading a tiny parameter for a dynamical field. And if this is really the whole source of the potential for the axion, the leading piece will be a mass term that is determined by QCD Stanton effects to be some QCD scale over the scale of the breaking of the symmetry. So you can think of this scale really as the coupling of the axion, and this is what encodes the QCD effects. So the way I presented this very well-known solution to the strong CP problem, it is already clear from what I said that the solution doesn't really depend on the detailed value of FA. So you can always make it so large that the axion interacts very weakly with the standard model and has a lifetime that can be comparable to the lifetime of the universe or even larger. So you basically introduce this new particle to solve a problem. Why not make it solve 2 problems and finding it a good dark matter candidate? Of course, I mean, it being stable is not the whole story. We also want a mechanism to produce enough relic abundance. And again, there are at least 3 known ways, but 2 of them are, well, one of them can only populate a small fraction of axion parameter space, so if you want to thermally produce it. Another one, the decay of cosmic strings, depends on the details of inflation and can be completely unimportant. The third one is the one I'm going to focus on and talk about. It's called misalignment production and can populate in principle all of the axion parameter space and has also some other nice properties. So let me tell you how this mechanism works. First through a cartoon, and then I'll be a little more precise. So the cartoon story is that when the universe is at a temperature that is much larger than the QCD scale, the axion has no potential. Then, as you approach the QCD phase transition, the mass term is slowly turning on to a value that is smaller than the 0 temperature value. And then eventually, once you go past the phase transition, the potential has completely turned on, and since the axion originally didn't have a potential, it could be living somewhere away from its minimum. So there's some energy density that is trapped in axion oscillations. And the energy density depends on the mass and on the cutting constant of the axion, and of course on the initial conditions that are completely unknown. So in principle, you can always match this energy density to be the dark matter energy density, just by fixing this parameter to whatever value you want. You can argue that in some corners of parameter space, this will induce some tuning of this theta bar. You can also argue that if the axion is a pure QCD axion, the potential is really a cosine, so this theta bar cannot be larger than 2 pi. But these are all details that are kind of unimportant to our calculation, and we can discuss later if you're interested. So let's just stick to the fact for the moment that we have this mechanism and we can in principle populate all values of MA and FA giving the correct relic abundance for the axion. So if this is the case, let's just discuss this mechanism with a couple more slides to see what the axion looks like. So what I draw here in pictures, it's really just an equation of motion that is the usual equation of motion given by the leading term in the relative to the potential plus some friction that is given by the expansion of the universe. And if you solve the equation, what happens is that the axion stays frozen for a certain time, so when the friction is larger than the oscillating term. But then, when the oscillating term starts to dominate, the axion starts to oscillate like a classical field. And the amplitude of the oscillation goes like the square root of the energy density, that for us is the dark matter energy density. And it's going to redshift like the square root of the energy density, so like z to the 3 ounce. So what we are working with is a classical field that oscillates with a certain amplitude that is given by a fixed number, the dark matter energy density, over the mass, and also over the dimensionful scale of the PQ breaking, because really what sets the strength of the axion coming to the standard model is this ratio that is proportional to this. And the point here is that this dimensionless coupling is really tiny. So if you sit on the QCD line, where all the mass comes from QCD instanton effects, this coupling is order 10 to the minus 22. So this is tiny but not completely hopeless, and there are many ways in which these effects have been proved in the past. So you can go to very high matter densities, like inside a supernova, and there's a bar that I'm going to show coming from supernovas. You can take advantage of some fields where you can measure things very precisely, for example, magnetometry, and couple this with the fact that you have a CPO effect in EDMs, so that it's linear in this coupling rather than quadratic. And that's basically behind many DM measurements that have been carried out and that have been proposed. The third way that has been explored in the past is to build resonant detectors and integrate for a long time, and this is the case of ADMX, for example, that is the classic axion detector. What I'm going to do instead is to go back in time. So as I was saying before, this guy redshifts as g to the 3 halves. So if the redshift is large enough, this effect is greatly enhanced. And this brings me to stating the main result. So this is the center of the talk, and after that, there are all technicalities. If you want, you can also doze off. But let's first state the 3 simple physical ideas that allow us to set a bound on this tiny coupling. So the first one is that if you go back to Big Bang nucleosynthesis, when light elements were formed, the redshift is huge. So you have an enhancement that goes like 10 to the 10 to the 3 halves. The second simple reason is that in spite of being so far in the past, we still can measure effects of BBM rather precisely. So the fractional uncertainty on the helium-4 abundance is of order 10% at 3 sigma, which is quite impressive if you think about it. And the third reason is that these axion effects, even if they enter quadratically in the production of like elements, they also enter exponentially. So you can compute the effect of the axion on the neutron-proton mass difference, and you get this number. And this number enters exponentially in the fraction of neutrons over protons that freeze out. And then, to a good approximation, all neutrons become helium-4. So this ratio really fixes what's going to be the fractional abundance of helium-4. That is what you measure. So putting together the huge redshift, the good precision of the measurements, and the exponential sensitivity, you can actually set a bound on axion dark matter.
So I guess I forgot why the axion causes neutron-proton mass difference.
Yeah, this is not obvious. It's the technical part that I'm going to talk about at the end. So it's really just doing some chiral Lagrangian gymnastics, and then at the end you see that it happens. But I'll do it in detail later. So these 3 simple physical reasons allow us to set a bound, and the bound is going to be on the product of FA times MA, just because, as I was saying, this is the relevant coupling, and this goes some fixed number on the numerator divided by FA times MA, where all the model dependency is encoded. So, but what I'm really going to show you is not the FA-MA plane, but rather the G sub D MA plane. And G sub D is just our scaling of FA that enters directly in the PDM induced by the axion. So, but before showing you the new bound, let me show you the old bounds that already exist. So here on the left, there are existing theoretical constraints or experimental constraints, and on the right there's the projected sensitivities of 2 experiments that have been proposed recently by Peter Graham and Sujit Rajendran. So as far as the existing constraints go, so here in purple you have just when F8 becomes larger than M Planck, which you can either accept or not, but you can see it in the plot at least. And then here in green, there's the region excluding by measurement of neutrino fluxes from the supernova 1987A. So the idea behind this bound is just that if the axion couples too strongly to the standard model, when the supernova explodes, a large fraction of the energy can be carried away by axions. And so the duration and energy spectra of neutrino bars would be very different from what we measured. And so you've just an upper bound on the interaction strength of the axion. So the true story is that if this particle interacts really too strongly, then the bound vanishes too. But if it interacts really too strongly, then you start seeing axions all over the place, even in meson decay. So for all practical purposes, for us, this is just an upper bound on the interaction strength of the axion. The second existing bound is an experimental one, but it's very conservative. So this is a rough estimate of the sensitivity of static EDM searches. So as we said at the beginning, the constant theta term and also the axion can induce electric dipole moments in neutrons and atoms. And this experiment measures static ones, while the axion gives you an oscillating one. And they measure static ones by integrating over long times. So here you're imagining that you are counting the oscillation at the end, not integrating over a whole period, but leaving a small residual effect. And that's what you get if you do this rough extrapolation. Also, at some point, the curve breaks because there you really have a static EDM. The axion oscillates so slowly that you see something static, and these experiments gain sensitivity. So I wrote it before, maybe I should say it again, but the frequency of oscillations of the axion depend on the mass. It's just really proportional to the mass. So before going to propose the experiment, let me tell you why I didn't draw more lines on this plot. So because there are well-known constraints on extra relativistic particles at various times in the history of the universe. One of these constraints is at Big Bang nucleosynthesis. The other two are when photons decouple and when large structures start to form. So in these two cases, you would see different distributions of galaxies or different distributions of anisotropies in the CMB if there were relativistic particles floating around at that time. And in this case, you would just have that Hubble at BBM is larger, and so the freeze-out temperature is smaller, and so again the ratio to which we are sensitive would change again exponentially. So in principle, there are three constraints that naively can be much stronger than anything I draw on this plane. But really, if you look at the numbers, they all roughly correspond to asking for 3 neutrinos and plus or minus 1. So the error bar is of order 1. It's really not so simple. I mean, some of them preserve 4 neutrinos, and I mean, cosmic data are a mess, but let me be conservative and say that we don't want more than 1 extra relativistic degrees of freedom around at least 3 times in the history of the universe. If you do that, then the bound is exactly the same as the supernova. So one of them is slightly below, one of them is slightly above, but they are so close that for us it really doesn't matter, because when I show you our bound, it goes orders of magnitude below this. So okay, this concludes the discussion of existing bounds. Going back to proposed experiment, so these guys basically are doing the same as the static measurement, only they designed the experiment to see an oscillating EDM. And they build it to be resonant, so they gain a lot of sensitivity. And this blue line is the first generation based on existing technology, and the red line is the second generation that is more speculative, and it puts together technologies that have never been tested altogether. And if you overlay with this hour bound, what you get is this. So there's the nice thing that it cuts much deeper in parameter space than existing ones. And notice that, I mean, the scale is logarithmic on both sides. So you're really going many orders of magnitude below and past the existing bounds. But what's possibly more interesting is that it's predicting that in the first generation experiments, they will hardly see anything until they get to the order of their sensitivity. Okay, so this basically is the main result, and I already told you all the important things. What comes now are some caveats and some technical discussion. So first, the first technicality is why the bound breaks here, and the reason is just that if the axion mass is too small, then it starts oscillating after BPM rather than before. So you cannot take advantage of all the power of the redshift. You're just redshifting up to when the axion starts oscillating. And so the other technicalities concern tuning. So as you might have noticed, the bound doesn't go all the way to the QCD line. So here it's where the pure QCD axion lives, where all the mass comes from the QCD anomaly. So the question is whether there are natural ways of reaching this parameter space rather than this parameter space. So we know that there are many attractive models that can live on this line, but is there a way to live above or below? And the answer is that naively, I don't know of any way of living above without tuning a lot. So because here, above the line, you're saying that for a given coupling, the mass that you get is smaller than the mass that QCD gives you. So if you want the QCD contribution to be there, you need something to cancel it against. And if you just add this another quadratic piece to the Lagrangian, when you go up to our line, you're already tuning a lot, much more than just not ignoring the strong CP problem would give you in terms of tuning. And what's even worse...
Don't the Stanford people claim that if you have more than one axion, then one linear combination will get the QCD mass and one won't?
Actually, I mean, we checked explicitly and it goes the other way, always. I mean, if you want to solve the strong CP problem, it always goes the other way. It's just algebra. I mean, we tried. Also, I mean, we thought about possible ways of evading this fine-tuning, but we don't really know of any. It's not a theorem, it's just that we don't know how to do it. But if you just naively think either about mixing or adding more strong dynamics, it never works. I mean, for the simple reason that you want to add this new strong dynamics at a higher scale, so you always want to have something heavier. And if you mix again, you always go below the line if you want to solve the strong CP problem.
I'm still confused about this. So, could you repeat somehow, I mean, what does the mass shift have to do with those arrows? I'm just not following the logic here yet.
Oh, I'm just saying that, so if you, let's say that all the axion potential comes from QCD. Then in this plane, you're just living on this line because the mass is given by the QCD scale squared over the axion coupling. And then, so I'm showing the whole plane, but really I don't know of a way of populating this region of the plane without tuning. Because in this region, the mass is smaller than the QCD mass. So you have a piece that comes from QCD, and you want to cancel it to get up here. And the only way I know of cancelling it is to add by end a PQ breaking piece to the Lagrangian that gives another mass. So I'm calling tuning this cancellation.
The other way, is that what you're doing?
Well, the arrows just means that here, the tuning is here. But yeah, the arrows, I mean, you can ignore the arrows. I'm just saying that this part of parameter space is tuned.
So you want to get a smaller mass.
Yes, than the QCD contribution. But still, I mean, you cannot even say that this thing doesn't couple to QCD, because to get the EDM, you want it to couple to QCD. So. Yeah, and what's worse is that, I mean, this piece doesn't have to be aligned with the QCD contribution, even in theta space. So you are also, on top of this mass tuning, you're also introducing again the strong CP problem. So in a sense, you made the tuning worse with respect to what you would have by just ignoring the strong CP problem. So then you might ask why I bothered with showing the bound at all. The first reason is, of course, that they're going to beat this experiment. So tuning arguments are nice, but if there's an actual bound from some measurement, it's better. So it's a good guidance for them. The second reason is that I think this point about the fact that there are operators in the Lagrangian that redshift is quite general and maybe can be used to put other constraints. And the third reason is that to get this bound, we have to compute the proton-neutron mass difference induced by the axion, And we notice that it's completely model independent at leading order, so it really is determined uniquely by the axion coupling to gluons. So it's not like the coupling to photons that is used in most astrophysical bounds and detection strategies that depends on the very model-dependent coupling to photons, as I was saying. This really just tells you how strongly the axion couples to gluons, which is what you need to solve the strong CP problem. So maybe it can open other avenues of detection or suggest other bounds other than ours. And so this is precisely the point where I'm going to spend a few more technical slides about. So to convince you that this is really model independent, let me do the algebra. So we start with the most general Lagrangian coupling the axion to strongly interacting fields in the standard model. So you just have the kinetic terms, the axion coupling to gluons, and here you have the model, all the model dependencies, so the coupling of the axion to the axial QUARK current. And what the final result is going to be is that the EDM coupling that is well known and was computed decades ago is proportional to this neutron-proton mass difference that I used to set the bound. And it's proportional to two factors that we know, so the quark masses and the pion decay constant. So to get to the result, the first thing you do is you do a field redefinition. Since I don't know how to translate this in a Kähler Lagrangian term, I want to get rid of it. And if you do the usual redefinition of the quark fields, this axial U1 shift is going to change the coefficient of this operator by this amount that is given by the sum of the phases we can choose here for the definition. Plus, you're going to get a phase in the quark mass matrix. So what you can always do is to fix the phases of this redefinition to cancel this piece. But then, of course, the axion doesn't go away completely, but it shows up in the phase of the quark mass matrix. So what we've done is, again, a field redefinition. We've used only half the freedom we had. So here I've imagined that there are only up and down quarks, but adding all the others doesn't really make a difference. And through this field redefinition, we moved the axion to the phase of the quark mass matrix. We've added another small model-dependent piece to the axion coupling to the quark current. And we got rid of this piece that we don't know how to handle in the Kähler Lagrangian. So, at this point, we know how to get to the Kähler Lagrangian, where the axion couples to pions and nucleons. And to do the exercise, let me first ignore this piece, which is what I want to prove doesn't matter. So if I ignore it, I can just write the quark mass matrix and the pion fields in the usual way, and then write down all the allowed operators in the Kähler Lagrangian. So nucleon kinetic term, mass, and coupling of the nucleon to pions to the mass matrix. Plus there are other things that don't matter for us that contain pion derivative interactions. So if you expand this Lagrangian in the axion and in the pions, what you get is that only this operator matters for us.
What is the lowercase u there?
The lowercase is just the square root of the
I see.
Yeah, so what I'm doing is precisely expanding the lowercase u and the quark mass matrix and getting that only this guy gives you both the pion axion nucleon coupling that gives DDN and the neutron-proton mass difference. And this is the result ignoring the model-dependent piece. So what the model-dependent piece does is to give you an axion-pion kinetic mixing and extra interaction with the nucleon current. So these extra interactions don't matter for us, but this piece in principle can give us a contribution of the same order as the ones that I just showed you. So at the beginning, I thought there was a deep reason why this piece didn't show up when one did the computation correctly. And the first thing that came to mind was that this thing might be unphysical, because as I was showing before, we used only half of the freedom in the filter definition, and if you, this half precisely, so if you use the other half, you can cancel exactly the coefficient of this term. Well, problem is that, of course, if you do this, then through the filter definition dependent pieces, this term is going to appear again in the mass mixing. So, unfortunately, there's no deep reason. It's really just a fact that this physical term contributes at an higher order. And let me show you why. So, if we take the full kinetic term, there's this small mixing that is model dependent of order f pi or fa. And you can easily show that this transformation, if epsilon is the same epsilon that you have here, diagonalizes the kinetic term regardless of what theta is. And if we fix this theta to diagonalize also the mass matrix of axion and pion, then you get that the total transformation basically transforms the pion in itself and transforms the axion in itself plus order epsilon of the pion. So, and from here it's already obvious why this doesn't matter. Because every time you have an axion in the CHIRAL Lagrangian, we have 1 over Fa. So the model dependent pieces always enter farther suppressed. So you're going to have 1 over Fa times this epsilon, that is all the order f pi over Fa. So this term is physical, but at leading order it makes zero difference. Okay, so this concludes all the technicalities and also almost concludes the whole story. All that is left is just this idea of converting Peter and Surgito experiment to a gravity wave detection experiment. So, yeah, which is not really in the main line of the talk, but since we have time, let me just flash this slide. So, as I was saying before, the axion oscillation frequency depends on its mass, and since we don't really know what the mass is, you can span several orders of magnitude in frequency. And the same is true for gravitational waves, but for different reasons. So the reasons are just that there are many different astrophysical sources, and there are also many different cosmological sources. And going back in time in the history of the universe sets a lower bound on the frequency. So, an upper bound on the frequency. So, the farther you go back in time, the higher frequency these waves can be. The second similarity between the two cases is that we have a classical field that oscillates coherently with a tiny amplitude. So the amplitude of the axion dimensional scattering is of order 10 to the minus 19. But if you were paying attention, you might notice that it's different from the number I gave you before. And the reason is that now I'm thinking about detecting this thing on Earth right now. So this is the dark matter density locally and not averaged over the whole universe. And this scattering is somewhat larger but very close to the typical dimensionless amplitudes of gravitational waves. The third point that makes me think that one might convert the experiment from axion detection to gravity detection is that the effect of the axion is to induce an oscillating EDM that goes linearly in the coupling. And for the axion, this is true for any EDM, basically, for any nuclear EDM. For a gravity wave, you can get the same effect if you think about a molecule having an EDM rather than an atom, because here you need a physical separation between the two charges that oscillates with the metric. However, this is all speculation, so I don't have precise numbers, etc., etc. But I think in the end this effect is going to be further suppressed because we're thinking about a molecule that is tiny compared to the typical wavelength of the gravitational wave. So what you're going to see is really just a tidal force that should go like length of the molecule over wavelength of the wave. So probably in the end this further suppression is going to make Peter and Sergit experiment not completely ideal, but since they can go even past, this is the number for the QCD line, but the sensitivity goes even past. So maybe it's doable, or maybe with a small technological improvement it's doable. And I think this is interesting in general, because in principle there's no reason why you cannot convert all experiments into gravity wave experiments, if you think about it a little bit. The other way around, unfortunately, is not ideal, and the reason is just that the action is a CP-odd particle, so typically with gravitational waves you see CP-even effect, so it's going to go like Axion squared, so here it's going to be 10 to the minus 40, and probably an experiment that is sensitive to this spin is not going to see anything. But still, maybe in the future generation of experiments we're going to have such a huge sensitivity that they can see also axions. Yeah, so we did some sort of rough estimates for LIGO seeing axions, but there's no... On the other hand, vice versa, I think it's interesting and should be talked about. So, okay, to conclude, I showed you this new constraint on axion dark matter parameter space, and unfortunately it doesn't go all the way to the QCD line, but still it's relevant to experiments that have been proposed. And what I find more interesting probably is that to derive it, we also derive this result for the neutron proton mass difference that ideally can be used for detection or other bounds, but again, as I was saying, it's going to be quite hard for detection because it's sensitive to this coupling squared. And yeah, so maybe astrophysical constraints or cosmological bound are more promising. We were thinking about, for example, I don't know, neutron stars orbiting for millions of years, billion of years. Maybe if you find a resonance there, integrating over such a long time, you can be sensitive, maybe not. I mean, I don't have precise ideas, but I think there's a lot of room for speculation, and so this made natural to show the bound, even if it's an attuned region. Okay, so this is all I wanted to say. Thanks.
So, your helium constraint, did that come from mainly the effect on the mass difference, or was there any part of that from changing NF due to production?
Yeah, so, and sorry, what do you mean by NF? You mean the... I see, okay.
Yeah, so basically, is production via the misalignment or any other mechanism relevant at all?
But it's relevant. Wait, you are asking me if it changes the weak interactions enough to change the freeze-out temperature, or is it another?
No, so...
You mean an effect?
Yeah, so is in that parameter space, is the axion thermally produced?
Yes, so
where
that
is that coming into the...
Yeah, that's what I was saying here. So,
okay.
So in the end, if you want an effective to be smaller than 4, here you're always fine.
Okay.
And up here you're gonna have problems both at BPN and later.
Okay.
So basically, where there's no line, it's fine. But yeah, I think I have a few more slides in the backup. Yes, so that's the story. So basically, an effective depends only on the axion freeze-out temperature. That in turn depends basically only on the axion decay constant. And then you can make 2 separate computations. One when the axion is thermalized by photons, and you get that your FA that are allowed by this bound of asking an effective to be smaller than 4 are of this order, which are pretty large and are well within that green region I was showing. And if you do the same with the axion thermalized by nucleons and pions, then again you get the same result. So basically, so anything above 1 MeV for the freeze-out temperature is fine, and you see that you're basically always above 1 MeV, no matter what is at fate.
Any other question for Raffaele? If not, thanks, Raffaele. So could you go back to your the mass splitting, your derivation? So
Which part?
so in the end, I'm trying to get the idea. So in the end, the mass splitting shows up because you have this power
by the end.
Oh yeah.
Well, it shows up because you have mu and then v that are different. So when
That's
you
right.
expand this piece, you get mu axion.
So
And the
your
axion
coupling has
Yeah, it has a part that is just central mass and a part that is mass difference. So also the central mass oscillates.
Is there a reason that you didn't do any of the other abundances like deuterium?
Well, there are two reasons. One is that they're measured a little bit worse.
So for deuterium, that's not really the case anymore, though.
Well, yeah, okay. The second reason is that they are not as easily calculable. For instance, I think it's completely unknown what's the effect of theta on the deuterium binding energy. Which for helium it doesn't really matter because it's really true that all the neutrons become helium-4. But then if you want to compute the details of all the other abundances, it matters. So
I see.
probably you can get if you could compute it, you could get factors of a few improvements in the bound, but still, it's an orders of magnitude game.
So it's really for helium, this is just affecting the fact that neutrons freeze out at a different temperature, whereas for deuterium, that's actually going to affect the binding energy as well, and you sort of don't want to touch that. Am I understanding right?
So for helium, it really just changes the initial conditions. Yes, but you can translate it into freeze-out temperature, but really,
Yeah.
So actually, the effect.
What I meant was what the neutron-proton ratio freezes out.
Yes.
Yeah.
Exactly.
Yeah.
So for helium, really, you can take this number and compare it with the detailed numerical calculation with all the neutron interaction rates, and it's exactly the same. Because all that deuterium does for helium is that it delays the moment where nucleosynthesis starts, right? So the only thing that the deuterium binding energy does for you here is that this ratio changes a little bit going from freeze out to nucleosynthesis, but it's a tiny amount. Instead, for the others, it really changes the rates, and you don't know how much it's left. The fact is that the helium-4 is basically 100%, and then the others are small fractions that are determined by also the deuterium binding energy.
Can you estimate what is the difference of thermalization of the axions after the decoupling or during decoupling?
Wait, what's...
When the axions would thermalize
Oh, yes.
relative to the decoupling?
Relative to the decoupling of... you mean what's... Okay, yeah. So the freeze-out temperature of the axions... So it depends, again, if you want it to couple to photons or not. But say you don't. Then typically it decouples between 20 MeV and much... This computation is for nucleons and pions. So it really doesn't make sense above a few hundred MeV.
Okay, there's a thermalization
Yeah.
for the carbon.
This is the thermalization versus FA.
Is this what's known as the Primakov effect also? Or is that different?
Well, this doesn't have the Primakov effect. It doesn't have the Q. I've not put in the Q axion, Q photon process.
Oh, okay.
But if you do it, then you get this. Look at this.
Oh, that, okay.
Yeah.
So that's what's known as the Freedom-Cough effect.
Yeah.
Okay. I thought this was just direct production by inverse decay.
The second one, yes.
Okay.
This one.
So I'd still like to ask about the Stanford claim. So if I
Oh.
have two axions, and they both couple to GG dual,
Yeah, so I had a couple of slides from the algebra, but they're not very illuminating. I mean, it's just, sorry. So, okay, so let's say you have two axions, and one has an extra mass. And then,
why does it need an extra mass?
well, I mean, if you just do this, then you again have only one axion that couples. I mean, this is effectively like having only one axion. Because only this
I thought
combination
that was
gets
their
the
point.
mass.
One linear combination
Yeah,
couples
but
to
then-
QCD and one doesn't.
Well, but yeah, okay. So let's say that one linear combination couples from QCD to QCD. Then this linear combination is going to have exactly QCD mass. So you're again on the line, and the other one
Yeah.
it doesn't couple to QCD, so it doesn't.
So it's
give
off
you
the line.
Well,
I
it's
thought
off,
that's what they're saying.
it's off the line, but since it doesn't couple to QCD, it doesn't give you an EDM. So I mean, it's so off the line that it's also off the plane. I'm just saying that, I mean, in this plane, this is really the coupling to GG tilde, because that's what gives you the EDM and our effect.
Okay.
So if you don't couple a linear combination, it's not even here.
I understand.
Well, that's what you do for forces.